If we can classify two triangles as similar, there are some properties that'll let us solve for missing side lengths. So let's talk about this terminology of just what does it mean for two triangles to be similar. So right here I have this picture, and let's say we got out our protractor and started measuring. Well, we have this large triangle 1 and this smaller triangle 2. In terms of angle measurements, if I measured angle B here, it would be pretty close to 45 degrees. Up here would be about 65 degrees. And over here would be about 70 degrees. So we have these three angle measurements coming through here. Now if I picked up my protractor and went to triangle 2 and started measuring angles, what we would actually see is that angle E here would also be 45 degrees. D would also be 65 degrees, and F would also be 70 degrees. So what this shows is that we can have two triangles with the same exact angle measurements, but as you can tell, if you got a ruler out and started measuring side lengths, totally different side lengths. What we end up with are these angles that what we're going to say is they correspond with each other. So what we can start to see is like angle B matches up with angle E, angle A matches up with angle D, and angle C matches up with angle F there. And those would be corresponding angles. So corresponding angles for a definition, what we'll say is congruent angles across two triangles. So again, congruent just means same measurement. So congruent angles across two triangles. So what happens when we do this is you have these corresponding angles. Then what ends up lining up is, it can be nice to have our picture like this so that the angles are kind of occurring in the same spot, like those 45 degrees are in the lower left, 65 degrees up at top, and 70 degrees off to the right. But then what we'll want to focus on is what's happening with the side lengths. Because in terms of solving for angle measurements, there's nothing to do with this. We'll just know that they're all the same angle measurements. But where we can start to see some properties is when we start looking at the side lengths. So what we want to think about is like this line that I just drew here is between the 65 and 45. So we can see where that side length lines up over there. Now in terms of visually right now, it doesn't look like anything's connecting those two besides the fact that they have the same angle measurements between them. Otherwise, they're two different measurements. The one from triangle 1 is obviously much larger than the one from side 2, and that's all we can say about it at this point. Same thing like between the 45 and 70, 45 and 70, those line up. And then 65 and 70, 65 and 70, those line up. So we can start to see is how these sides line up with each other, and those will be called corresponding sides. So that side AB here is corresponding with side DE. So in terms of a definition, it'll just be the sides that line up between the congruent angles. That line up between, and sorry, not congruent, the corresponding angles. So that's some terminology. When we have similar triangles, which again, similar triangles just means two triangles with the same measurements. Sorry, with the same angle measurements. If we have similar triangles, then having these corresponding angles line up and corresponding sides, there's going to be properties that we can use specifically for solving for side length. Now, with this, let's talk about the property. And sometimes this can be a bit confusing in terms of visually how we can have the same angles but totally different side lengths. And what you want to think of here is that it's like we're like maximizing and minimizing an image. It's like if you're working with a copier or you're scanning something, you could like blow it up by 100% or shrink it down by 200%. You have these options for shrinking and enlarging, and that's what's happening here. And when we do that, the angle measurements stay exactly the same, but the side lengths change. And the key is that terminology that I used of like maximizing by 100% or minimizing by 200%. There's going to be this consistent ratio that's used. Are we doubling everything? Are we making everything smaller by 1.5? There's going to be this common factor that is used to make it larger or smaller. Because for those angle measurements to stay the same, we'd have to use the same sort of shrinking or enlarging for every single side length that we're using. So it's this ratio that we want to use to help us solve for different side lengths. So for properties of similar triangles, what we're going to do is first make sure that they are similar. So we'll make sure the angle measurements are the same. But then what we'll want to do is focus on corresponding side lengths. So like I drew up above how AB corresponds with DE and BC corresponds with EF and CA corresponds with FD. So like I was saying up above there, it's like how AB shrinks down to DE, whatever scale is used, the same scale is used to take BC and shrink it down to the size of EF. And the same scale is used to take CA to shrink it down to FD. So what we need to do is figure out what is the scale so we can apply it and solve for the different side lengths. So we do this with ratios, which ends up being a fraction. So the property that we're going to use, it sets up equivalent, meaning same, the idea that we're using the same ratio for each side length. So we're setting up equivalent ratios of side lengths. So like I was saying verbally, and how we're going to translate it to a formula, is how we took AB and shrunk it down to DE, and in this case it's shrinking, but it can also be enlarging. What we're going to do is create a ratio. How AB changes to DE is the same as how BC changes to EF, which is the same as how CA changes to FD. So we get these three ratios that are all the same. One thing you need to be is consistent about what's going in the numerator and what's going in the denominator. Notice that the side lengths coming up in the numerator all coming from triangle 1, and in the denominator all from triangle 2. This should happen every time. When you have your two triangles, the numerator should consistently come from the same triangle and the denominator should consistently come from the other triangle. You don't want to mix it up because that'll mess up the ratios. You'll actually be using the reverse of the ratio and you'll get the incorrect answers out. Some notation that you'll see with triangles. So like we have triangle ABC up here for triangle 1. If I wanted to write notation to say that's similar to triangle 2, for notation, similar would be kind of this squiggle between the two, and then triangle. And then where I wrote the notation for the first one, just ABC, how I write the second triangle is very important in that you want to write it in terms of corresponding angles. So like I wrote A first, so D would have to be first. I wrote B second, and that corresponds to E. I wrote C third, and that corresponds with F. It would absolutely have to be in that order. The idea being that when we have this notation, it's giving us a setup for our corresponding side lengths. How AB works with DE, BC works with EF, and then CA works with DF. So, or FD. Order of the line segments like FD versus DF, same thing, but having the lineup of these triangles and being similar, you want to be careful of that order, and it will tell you which sides are lining up with each other. So one little piece we need to talk about, I'll talk about the calculator a little bit here too, But with these ratios and solving ratios, we need to review a concept that's covered in algebra of cross multiplying. So we're going to end up with these, we'll have an unknown side length, but we'll have all these other numbers. So we'll end up having this fraction equaling a fraction. And there are, of course, a lot of different ways to solve these. In fact, this property that we're learning can even look different. If you find a different way to solve that makes more sense to you, absolutely use it. In algebra, there's always 100 paths to the same answer, and we're all coming from different backgrounds of algebra, so use the tools that you have. But I'm going to show cross multiplication. So if we wanted to solve this x over 2 is equal to 3 over 4, cross multiplying, what it lets you do is we're going to multiply across the equal sign. So we're going to drop down the equal sign. That has to stay there in our solving. What we'll do is across the multiplication, we're going to be making this x here, like this. Now we're going to take x and 4 are going to work together, and it's going to be multiplication. So we're going to have this x times 4, and then on the other side of the equation, the 2 times 3. So this ends up being 4x is equal to 2 times 3, which is 6. And then solving for x, we just need to divide out that 4. So we'll get x is the 6/4. Now, let's talk in terms of, especially with MyOpenMath, sometimes it'll tell you how to format your answer. If it wanted a fraction, you should be able to type in 6 divided by 4 and that'll work. Sometimes it'll want a reduced fraction or a decimal. So there's a few ways to go about that. I'm going to show you with the online calculator Geogebra of how we'll do this. So with Geogebra, if you go to this website, geogebra.org, there's this scientific calculator here under new math apps. And then what we could do is just type in our fraction. So there's this button here that can separate your fraction 6 over 4. So 6 over 4, sorry, it was being a little glitchy there. So there's our decimal, 1.5. So that would be an answer. Or what you can do, and if we hit the enter symbol here, it'll finish up that equation. So you can see as it has our equal sign there, or there it's showing a rounded, even though that is exact 1.5. But if you wanted to know what the reduced fraction is, and you can reduce by hand, but there's going to be fractions where it might be hard to tell if it reduces or not. So what I like about GeoGebra here is if you press this equal sign off to the right hand side, it'll switch it to the reduced fraction. So then I'll give you the exact answer, and then we'll give you a decimal solution. So you could switch between those two. So when you're working on homework, depending on how it asks you to format the answer, you can have your two possible solutions there of the fraction form or the decimal form. So if we wanted a reduced fraction, we'd want to punch in 3/2. If we wanted the decimal, 1.5. All three of those are the same exact thing. It just kind of depends on what we want for a final answer. All right, just one more sample of this, of how we're going to cross multiply. And this only works when you have a fraction equaling a fraction. If we had anything like adding on the outside or subtracting, this doesn't work. But if we have fraction equals fraction, which is going to happen with these similar triangle cases, it's perfect. So we're going to have 3 times 5 on one side of the equation equals x times 8 on the other side of the equation. So this will be a 15 equals 8 times x. We'll want to divide both sides by 8. So in terms of a reduced fraction, it would just be 15 over 8. If we wanted a decimal out, and let's actually go back to GeoGebra, just since this is how it'll show up in your homework, 15 divided by 8. So 1.875. So that would be the full decimal, and that would be exact. That works great. But sometimes they might tell you how they want you to round it. So let's say they wanted us to round to 1 decimal place. There are a lot of ways to think about this, but what I think about is, okay, we want to round to 1 decimal place, so I want to cut this up so that I only see those first two pieces there. I'm going to have 1 point, but then wherever I'm cutting, I need to be careful of, am I going to round up or down? And that's where you look at the number just to the right of where we're cutting off the number. If that number's 5 or above, we're going to round up. If it's 4 below, that number stays the same. So if it was 4 below, I'd write 8 next, but it's a 7, so we're going to round up, so it'd be a 1.9. So just a little review of how to round solutions. All right, let's do 2 examples with taking this method and applying it to our ratios. So what we're going to do is assume these 2 triangles are similar, and what you can see is they're lined up already with the right angles in that lower left-hand side. So that means like we have our hypotenuse and we have our hypotenuse, so those are going to be corresponding sides. We also have this leg here corresponding with that leg there. And then we have the other leg, but they didn't include the numbers, and we don't really need it. All we need is 2 pairs of corresponding sides. So now I just need to create my ratios, and there's probably about 4 different ways to do this, and you just need to choose some pairs. So no matter what, I need 66 and x to go together. It doesn't matter if it's 66 over x or x over 66. What's key though, like if I choose to go 66 divided by x, what that does is it sets my numerator to come from this first triangle, and my denominator has to be from this second triangle. So you just want to be consistent that when I make my next fraction, so I have my equal sign, then I have to start with my first triangle. So it would be 42 over 35. So I would set up my ratio, and then it becomes a cross multiplication problem. So I'm going to be taking 66 times 35 on one side of the equation and x times 42 on the other side. So 66 times 35 is 2,310, and then 42x, and then divide both sides by 42, and that will give us 55. And then they're giving us units here, so we're getting 55 out, but it's a good idea to always include your units if they're there. So 55 feet would be our solution to make that work out. All right, one more example here. The triangles are lined up. They're telling us that they're similar. So that means this side is going to correspond with that one, and this side will correspond with that one. And then we can start to make our ratios. I'll go y to 15 is equal to 42 to 63. And then it'll be cross multiplication. So y times 63, so 63y, equals 15 times 42, which is 630. Divide by 63, divide by 63. So this will be 10, and then just grab our units, which in this case is meters. So that's how we can solve similar triangles using ratios and cross multiplication.